So, very warm welcome to all of you from the Goa ACM chapter. So, this is, and thank you, Sir Professor Ashwin, for giving us the talk today. And this is the second talk we are having since we have restarted with our chapter. We have a few things planned for the entire year, few talks planned for the entire year, and we also have our Vice Chairman Neha. We plan to start a tutorial series for students in various areas, and the next tutorial that will be conducted by Neha will be about introduction to discrete events. Okay, and so I would highly encourage you guys. We'll be sending out a flyer for the same to please join that. And one of the other upcoming events is about the ACM student chapter Manipal University, right? We plan to have a ACMW national level virtual hackathon. We'll be sending information regarding the same. It's also there on the ACM Facebook page. I would encourage you guys to be members of that group. And the domains are in healthcare, security, smart systems, fintech, and I would encourage you guys to the students to please participate. And I now hand over to my professor VVK Kamath to introduce the speaker. Thank you, sir.
Okay, thank you, Maria. On behalf of ACM Goa Professional Chapter, let me welcome you to this second talk in series titled Machine Learning for Humans. And today's speaker is Ashwin Srinivasan, a professor at BITS Pilani Goa campus. But before I introduce the speaker, let me just inform our audience that since July this year, we have revived our chapter activities. Last year, due to pandemic, we couldn't organize many activities. And now ACM Goa chapter has a young, energetic, all women's team as its office bearers. And we plan to organize at least one event every month. Just now, Maria mentioned, we just had a meeting before this talk, and we are thinking of having these tutorials, which will be of interest to the students. There are 2-3 exciting events that are lined up for the next couple of months. We have a second computational thinking conference scheduled on 2nd and 3rd of October. And there is Compute 2021 that is going to be hosted by Delhi University from 18 to 20th November. I would request the students and the participants to visit ACM India website once in a while to see what kind of activities that are being hosted and which might be of interest to you. So currently, AI and ML are buzzwords, and every industry worth living want to apply AI ML techniques for improving productivity. Today's talk is more about intelligent assistants, that is IA, and artificial intelligence, AI. On a lighter note, a decade back, to Indians, AI and IA would mean Air India and Indian Airlines. Unfortunately, one of them has closed down, and the other is on the way and is in the trouble. Now, let me introduce you the speaker. Ashwin is a class of 1981 chair professor of BITS Pilani. What that would mean is that the students from the batch of 81 has instituted a chair and Professor Ashwin has been appointed against the chair. Ashwin received his Ph.D. from University of New South Wales, Australia in 1991. And soon after that, he joined Inductive Logic Programming Group at the Turing Institute, Scotland, and worked on the development and application of inductive programming. From 1993 to 2003, Ashwin was at the Oxford University Computing Laboratory as a research fellow and then a lecturer at the university. In 2003, he moved to IBM Research India as a research staff And in 2009, he was awarded Ramanujan Fellowship by the Department of Science and Technology, Government of India. Between 2010 and 2012, he joined as a professor at the newly formed South Asian University in Delhi and became the founder dean of the Faculty of Mathematics and Computer Science. Before joining BITS Pilani, Goa in 2015, Ashwin was a professor of computer science at IIIT Delhi. From 2020 onwards, he has been the head of the Anuradha and Prashant Palakurthi, a newly established Center for Artificial Intelligence and Research at BITS Goa campus. I have known Ashwin from 2015 as a friend. We had a common friend, and that's how I came to know Ashwin. And we have been since then, we have always shared with each other the joys and the pains of being academicians. With that brief introduction, let me welcome Ashwin to deliver the talk. Ashwin,
Yes, thank
floor
you.
is yours.
Thank you, Venkatesh. Yes, I'm afraid I cannot project my slides due to some technical glitch on my browser. So Venkatesh is projecting for me. We sort of anticipated this might happen. But Venkatesh, is it possible to put your thing on full screen or anything like that, or is this the best we can do?
This is the maximum.
Control L would do something, I suppose. But like turn it off, perhaps.
Okay,
yeah,
Control L. Yeah.
Yes, this is better. Yes, well, thank you, Venkatesh, for that introduction. I'm sure we've known each other for longer than 2015. I think 2015 was when I moved to Goa, but I think we knew each other even before then for some time. But today's talk, I'm going to talk about machine learning for humans, as the title says. So I will say next slide, and Venkatesh will presumably press a button. As Venkatesh said, what we are besieged, as I'm sure you're aware of, the fact that, as the shoe company says, that we have to just do AI. This is what this is the thing to do. Everybody is doing AI, whatever that means. Which means what? Machine learning. It means doing courses in AI. It means doing writing textbooks in AI. It means getting highly paid jobs in AI. It means all sorts of things. So what exactly should we be doing in AI? Next slide. So just do what exactly is a question that probably is something that concerns many people. So my talk actually is not exactly about many of the standard kinds of things that are going on in AI, but it is a talk nevertheless of some importance to it. I've deliberately called it IA, somewhat inspired by the Air India and Indian Airlines story, I must say, because it is something that struck me at the time when I was labeling this. So this is about building intelligent assistants that have basically humans or people involved in a loop in which machines and people are collaborating with each other. So an example of this is in the next slide, which shows one possible way in which this happens. There are many ways, of course. I mean, it is almost axiomatic nowadays to say that humans and machines talk to each other. They do so in so many different ways. The ways that I'm particularly looking at is in ways in which machines are not just doing things like providing interfaces to data or storing things or acting as word processors, but are actually actively collaborating with people in discovering new things. So an example of this is in scientific discovery. So this picture is an example of that kind of area of collaboration, in which, say, a biologist normally would get observations from the real world and conduct experiments and think about things and come up with models for biological systems. But now a biologist has the option of really not only conducting experiments on real world systems, but he or she can also talk to a machine, which could be given data, it could be given domain knowledge, and it may produce models and explanations. Now, the context of why these machines are actually useful is because we are not able to deal with the scale and diversity of data that is now being generated, largely because of several advances in sort of technology, of sensor technology, of storage technology, which means that things are progressively more and more instrumented, so we have more and more data. And humans are not very good at keeping so much data and making patterns out of very large amounts of data. We're very good at smaller amounts of data. There are now programs, as many of you know, that can handle the data, but they construct models that we do not understand, which leaves us with two options. And both are actually real options. It's not that one of them is a dummy option here. The first option is that we don't really need to understand the models that are constructed. We just need to use the models. And the second option is that we do need to understand the models. So a kind of third option of we need to understand it somewhat is not something that I'm considering in this particular talk. But for the moment, let's take this simple-minded view that there are only these two worlds that we need to operate in. So the world that I will be talking about today is on the next slide, which is when option one, which is that we don't really need to understand, isn't really an option. But as I said, there are cases where that is an option, and I'd be happy to talk about that at some other point, but not today. But examples of when option one isn't an option is abound as such as we look around. In science, as I said, it's possible for models to construct machines for natural phenomena, which allow us to help understand how things are as such in the natural world. In engineering, models can be constructed by machines for monitoring phenomena to help us identify faults, to identify systems, the actual design of a system, like what is inside a black box, or to assist even in the design of new systems. In business, for example, models are being constructed routinely to model you and me. I'm sure Amazon has a model for you and me, and certainly they have for me, because they keep telling me what I should and shouldn't be doing. So these are models which presumably we would like to be able to understand why they're telling us what they are. So there are other examples which I won't list out further. So the requirements, if you think back to that picture with the biologist, is that we have to be able to tell these machines what we know in a sufficiently precise way, and that machines will have to be able to tell us what they know in a sufficiently understandable way. This seems sort of a reasonable set of requirements for dealing with issues that will arise when you have human-machine collaboration in this way. Now, none of this means that machines have to sort of represent and process information like us. It's just a communication requirement that I'm laying out, that we have to be able to tell things that machines can understand. It doesn't look like random stuff for them, and they have to be telling us something that we can understand, so it doesn't look like random stuff for us. So next slide. So before we start, I suppose I should, it would be helpful if I told you what I meant by a model building machine. So this is minimally what I mean. A model constructing machine is one that learns, in the sense that it's some kind of box which takes data in and produces as output some predictions and some explanations. And it may have some other things going into it, like a kind of utility or a loss function, and some structure and parameter specifications which will define how the model sort of actually is as such, the kind of class of models that we're dealing with. So minimally, this is the sort of thing that I'm talking about. So given that, let's talk about what it means to tell machines what we know. So next slide, which is just a dummy slide. So so the first part is how to tell machines what we know. No, a slide before this, Venkatesh. No, before.
Okay, so just a minute.
Right. Now, no, hang on. Okay, yes. So there are a number of different ways in which we can tell machines what we know. We can tell them, let's start from the left. We can tell them, here I've used the term B for background knowledge or background information, and T is some kind of transducer or something that changes stuff. One way we can tell machines what we know is somehow to alter the data that they take in. Another way is to alter the loss function. And some other ways, obviously, where you can use the background knowledge to influence the parameters or the structure of the model. So these are basically the ways, seeing that that's the kind of machine that I'm looking at. These are the ways in which we are going to be able to distinguish, use the kind of information that we have. So we have to devise ways in which we can do these sorts of things. And many of these, let this plane go overhead. Those of you who are in Goa will know that we are pretty much adjacent to the airport, so there's plenty of noise, plane noise. Right, so, and many of you would know that any number of these things have been routinely done in many ways, using domain information to devise a loss function is a very common activity for people involved in optimization, in machine learning. to bias the parameters or the structure is a very common. So biasing the parameters, for example, is what happens in transfer learning. In biasing the structure is something that so by these forms of bias, you could always think of it in a sort of Bayesian sense, and this has been going on for a little while. I'm just going to tell you a little bit, not in terms of details, but just give you an example of how we can use domain knowledge to change the data as such, which is sort of less routinely done. So next slide. So I'm only going to give you results, and then I'll talk about details in a sort of question-answer session, or point you to the papers that are involved. So this is the only kind of talking to machines that I'm going to be reporting on in this talk. An example, we've been doing this sort of thing a little bit here in the AI Center in Goa, and here are some examples of doing this kind of activity. So if you go to the next slide. Okay, what do I mean by telling machines what we know in the form of data? So we want to be able to take into account information like this, that we want to be able to say that for inhibiting this kind of protein, the presence of some kind of peroxide bridge is relevant. The target site is at most 20 angstroms and things like that. So we need to be able to tell machines what we know in a sufficiently precise way. So I've written this in English, but actually what we deal with is not so much in English, but we write it as sentences in a formal logic. Now, next slide. Here is an example of some results of doing this for an area related to the previous slide, which is in the area of drug design. So those examples were from that kind of area. So here you see two kinds of graphs. You're not supposed to actually concentrate on the numbers, but on what they look like. So both of them have a flat line, the blue one and the white one, and then they have a sort of zigzag, sort of jagged line on top. And these are results from two different kinds of deep networks, a graph neural network or a deep multi-layer perceptron. The flat line is when we don't give it any kind of domain knowledge by way of information about the drugs that that may be relevant to them. Now, what are the things on the x-axis? There are actually quite a lot of data sets. There's about 73 data sets. So this is not a small study involving 3 or 4 different or 5 different data sets. There are actually 73 data sets running into about 250,000 or more compounds, and to deal with their activity. So the flat line is when we don't provide any kind of domain knowledge, and that's the predictive accuracy, which we'll call 1. And the jagged lines are what happens when you do provide domain knowledge in a form that alters actually the data provided to these deep networks. And you can see that there is a pretty serious increase in the predictive power of these machines. This is slightly misleading over here. It looks like it is the case that the increase is greater for the MLP, but actually the GNN actually does perform better overall. So the 1 for the GNN is much better than the 1 for the MLP in general. But for both of them, across 73 different problems that we tried it on, and we've tried it on other things as well, which are not drug design type problems, there is a substantial increase in the predictive power. Now, somebody has raised a hand. I think I'll leave questions right to the end, if that's okay, Maria. Or
okay.
Because I don't know how long is the talk, Venkatesh? Is it half an hour or 1 hour?
It's you can go on till 45 minutes. You normally have the talk.
Okay.
And then
so let me press on. So this is an example of the benefit that you can get if you actually communicate something of relevance to a machine. So I'm going to put forward a conjecture on the next slide, which I will call the predictivity conjecture, that if a machine's predictivity increases, then the human knowledge provided was sort of machine understandable in some way. Now, it's just a conjecture for which I'm proposing here, partly in fun, but partly something to think about. I'm not saying that. Remember, if I say something like this, then it means that if the predictivity doesn't increase, it doesn't mean that the human knowledge wasn't understandable. And similarly, so it's basically saying that for increase in predictivity is a sufficient criterion for it to be machine understandable. Otherwise, there's not much that a machine has been able to do with it. Or conversely, that machine understandability is a necessary criterion. The machine has to be able to make sense of the data that has been provided for its predictivity to increase. So it's a necessary condition for predictivity to increase. So I'll leave this for you to think about, either in the talk or for later, and go on to the next part, which is the other side of the story, which is when machines tell humans what they have found. So how should machines tell us what they've found? One way is the one on the left, or another way is the one on the right. And I'm being deliberately unfair here, because I know that most of you, other than one or two people whom I know, who actually prefer the one, the one on the left. I think many of us would probably prefer the one on the right. So how should machines talk to us? I'm going to take it as axiomatic that they should talk to us in something like the thing on the right, rather than the one on the left. And in fact, both of these are exactly of the same model, but the one on the right was extracted after, as a sort of post hoc explanation of the model on the left. Next slide. So this distinction between black boxes and white boxes has been made by many people. That an example of black box type ML is provided by a deep network, which has high predictive power, low, it is claimed, explanatory power, need large amounts of data, and they use limited use of prior knowledge. Although, as I showed you just now, it is possible to use prior knowledge in many different ways for a deep network. There's no particular reason why it can't use prior knowledge. Certainly in the loss function, certainly in the parameters and the structure, and even in changing the data that it is seeing. But it can work also with very low-level data. The logic-based models, like the ones that are kind of typo predictive power, may not be as high, although that is also can be contested. Claim is that they have high explanatory power, but I will again put forward something which will have something to say on that. and let this plane go overhead. And that they can use prior knowledge and may not work very well with very low data. So these are sort of the usual claims, but none of these, I should say, are cast in stone. I'm sure there will be someone, if not in the audience here, but somewhere, who will be able to contest each one of these in sufficiently robust and very believable way. But these are the stereotypes, kind of myths and legends that accompany black box and white box ML. So let's go with the stereotypes for a little bit. But there are problems if when low explanatory power requiring large amounts of data type machines are not the kinds of machines that we want to deal with when we're doing this human machine collaboration. So on the next slide. Venkatesh, yeah. So there are problems for which complete black boxes are not what is required. So you either go with a white box where you get both prediction and explanation. I've dropped out the loss function, parameter, model structure, all that stuff, and just generally said that some domain knowledge goes into the machine, however it goes in. Or you have to build some combination box which basically has the predictive capabilities of a black box and the explanatory capabilities of a white box. And these sort of things can be done and are being done, but they're not the full story. I'll come to the sort of other parts of this story in a moment. But these things are very possible. I'm going to give you an example of a simple kind of simple-minded way of doing a black and a white box combination. Not the only way, but a way which was effective. So on the next slide. So an example of a kind of gray box that we built recently for some analysis of COVID X-rays was to have a bunch of black boxes, which were deep models, which extracted features from chest X-rays. And then those features were used by a white box decision tree model to come up with a COVID prediction. What features did the black boxes extract? Well, and there is the interesting and useful thing is that the features that the black box extracted were features that we knew were important to a radiologist. So it's not just any old features, but features that a radiologist could reason about. And how well did this do? In fact, this kind of approach did just as well as an end-to-end black box model, which had a deep network, which just went from X-rays to prediction. So there was pretty much no change in predictive accuracy by doing it in this hierarchical fashion. Now, there's nothing especially earth-shattering about this hierarchical way of doing it. Those of us who have seen computer vision developed from, I don't know, Ballard and Brown type days will recognize that this is just standard way of doing computer vision, which is, you start by extracting low-level representations and then use those to build high-level models. Next slide. So the kind of explanations that a machine can then give is, a sort of textual explanation of how the tree built its model by saying, things like airspace specification probability was low, and some other thing probability was low, so therefore it was something or the other, and a kind of descriptive textual a description of what the different kinds of features were and what their probabilities were, so on. So this is something that is very easily extractable from a machine of the kind that that I was talking about. Now, the interesting thing is on the next slide. It's not that these things are possible. So here were results from two different radiologists. The two tabulations, again, the numbers are not particularly important for the reasons that I'll come to in a moment. But what are these tabulations? So these are tabulations of the assessment of the explanations by radiologist 1 on top, radiologist 2 at the bottom. So let's look at the first column. Radiologist 1, white, in the white table, says that he or she, well, it's he, they're both men, thought the model was correct and the explanation was sufficient some proportion of the time, large proportion of the time. At other times, he thought it was, even though the model was correct, I mean, the prediction of the model was correct, he thought the prediction of the model was correct. It's not that thinks the model was correct, but the prediction was correct. But the explanation was insufficient or incorrect. Now, there's also times when the radiologist thought the model was wrong, and in those cases, he thought that the explanation was insufficient or incorrect. And similarly, when he was unsure whether the model was right or wrong, he thought that the explanation was largely incorrect anyway. Similar sort of story, but more polarized for the blue radiologist, that both of them are able to say when the explanation is sufficient, insufficient, or incorrect. And usually they go with insufficient or incorrect when they think the model is wrong, and they're also unsure when about the model some of the time, and when they're unsure, they almost always think that the model is explanation is incorrect. Now, what's the interesting thing here? The interesting thing here is that actually that we can do this at all, in the sense that the radiologist is able to do this at all, is the interesting thing, at least for me, that he has been able to say something about this explanation. Which brings me to another conjecture that I'm going to make about machines talking to us, which is on the next slide, which I call the explainability conjecture, is that if a machine's explanations are refutable, then they are human understandable. Now, this is slightly odd. It may strike you as less sort of immediately apparent than the predictivity conjecture I had earlier. So what it's claiming is that really for humans to understand the explanations from a machine, we must be able to, if you cannot understand it, then we cannot refute it. So we must, so refutability of an explanation, somewhat in a sort of somewhat like scientific hypotheses, are I think important for the kinds of explanations that we receive from a machine. So we should be able to say, I think this machine is wrong here. Now, if you present, and we have tried this, if you present a person like a radiologist with a set of machine-based explanatory criteria, they are completely bewildered and they have no idea what to make of it. And say, well, I don't know, whatever that means. So that's sort of not what is good. I think what they have to be able to say is, yes, I think this is getting it right for the right reasons, or it's getting it wrong for the wrong reasons, or right for the wrong reasons, and so on. So they should be able to reason at that level. Next slide. But as I said, on the explanatory front, this is not the full story. there are three sorts of things which are happening, which are moving forward in very interesting ways. And I'll give you examples of these. Ross King and colleagues at Chalmers are adding active learning capabilities to white boxes to allow them not just to talk to a biologist, but to talk directly, to do the experiments directly. So they are not just relying on a biologist to devise the experiments, but they're having machines do the experimentation themselves. Pete Clark and colleagues at the Allen Institute are adding language capabilities to black boxes to allow domain knowledge to be entered in a natural language, with using natural language. So we did it using a logical representation because we were communicating large amounts of scientific knowledge about what constituted benzene rings and alcohols and ethers and what was important and what was not and so on. But realistically, in the end, it is not really feasible for other than in sort of, unless you have prepackaged libraries to do it in that way. But it is feasible as we go on with humans in the loop that people will be able to talk to machines in a natural language. And for that, the work of Pete Clark and colleagues is making great headway. And Stephen Muggleton and colleagues at Imperial are looking at a theory of explanations which allows them, I gave you a kind of proof theoretic way of looking at the utility of explanations, that to be useful, they must be refutable. Stephen Muggleton and colleagues are doing a kind of semantic version of this by looking at characterizing beneficial and harmful explanations for humans, for human in the loop type applications. And so these are three very interesting ways in which the results to and from machines in this collaborative manner are being changed in very important ways. So next slide. So in summary, so if you can imagine a learning machine that suggested, for example, to Kepler that an ellipse should be fitting Tycho Brahe's data of the orbit of Mars, or Ramanujan that numbers of a particular had a particular pattern, or a biologist on how to modulate the immune response to an autoimmune disease, or to you on what to read next because you it looked like you were a Trotskyite. If you think that these sorts of collaborations are interesting and important and could achieve useful things, then you have to think about machine learning for humans. And that is the end of my talk. I think I have a slide of acknowledgements, which are for a number of colleagues and experts who helped us with all of this. Institutional acknowledgements to various institutions as well who were involved, and some results. The results on these on the slides here are from some papers which are there at the end of this talk after this slide, I think. So these are some references just for the results that I mentioned. There are lots and lots of other work. As I told you about the three different things that are going on, which I found interesting, but there's lots of other work, and I'm sure you'll find it, but these are the ones related to the results that I've mentioned. I'll take questions if anybody has them.
I request the participants, if you have any questions, you can ask the speaker. Yeah, Sheshanshu, you can go ahead.
Yeah. Hi, Ashwin. I have a question. So it's regarding that slide that you were showing with GNN where you you are demonstrating that the predictive power has increased, right? I mean, I'm not bothered about how much the predictive power have increased. Rather, interested to know. There are things like classifier confidence, right? There are some interpretability tools like Shapley and Lime, and then there are, in fact, within the construct of loss functions, you can think of some loss functions which are robust to level noise and things like that, and from which you can define new metrics such as confidence rate or retention rate, right? So the point is, when you have involved humans in the loop, right, and your predictive power is supposedly increased, right? Have you compared or have you computed any classifier confidence metric when the humans in loop module have been engaged?
Okay.
Because it could have the same problem as the raw predictive power, right? 99% accuracy with less classification confidence.
Let me take this one step at a time. This is an assessment of what happens this is not Lime type things don't come into this, because this is not about the explanatory thing. This is about what is going into the machine from the biologist into the modeling system. So it is actually about the domain knowledge that is being provided into the system. So it's with and without that link, what happens. So the increase in predictive power is just being judged across a range of different problems with and without that link. The question of whether the machine becomes more confident or less confident on a particular data set with and without the machine is without that knowledge is not something that we have computed. What we have computed is only whether there wasn't any observable effect or not. I think in the short, that is the answer to your question. But the fact, so what we did see is that almost across the board, there were improvements in the predictive power, but there were cases where the predictive power sometimes went down as well, but they were quite very few in numbers.
I wouldn't bother much about the predictive power going down by a fraction or so.
No, I agree.
Yeah, but do you think it is possible to compute the classifier confidence? I understand what you are doing here. There are some features which become more explainable. The kind of features that you extract out of this,
So we don't actually, we don't do the feature extraction. What we provide are logical relations. The machine does the feature extraction internally. So the question is, whether it actually extracted meaningful features or not is something which we have not been able to solve that problem yet. But I think it's not just the confidence that one thing that we are quite sure is that the confidence of the person involved will be much higher if the machine can actually inform him or her of why it actually improved its predictive accuracy in this way. So
yeah, completely. Okay.
Any more questions from participants? Yeah, please go ahead, Naigam.
So, yeah, Ashwin sir, so my question is that we know about, as you mentioned in the previous discussion as well, that we know that there's a trade-off between the performance and the explainability here. So so there are lots of techniques coming up which basically can give you explanations of sorts and can give you insights into the model, right? Now, what are your thoughts about as in verifying whether this particular explainability technique that we are using, um, whether it's as in adding any more bias in the model, or it's absolutely 100% correct or not?
So as I said, there are two options here. So let me talk about the work of some other people, which first says how to assess whether the explanation is useful or not. So the theory of explanation that Stephen Muggleton is proposing is one where the performance of the person either improves or gets worse having seen this explanation, roughly speaking. I mean, there's more to it than that, but roughly speaking, that's what he's suggesting, is that that explanations produced by a machine can, so it's routinely generally thought that is very important for machines to produce explanations, but actually few people have thought that these explanations can cause harm as well. And he's one of the people who has thought that it can be harmful in some cases. So, for example, a perfectly good biologist may start doing really badly, or a perfectly good radiologist may start doing very badly by relying on some explanations from a machine. So there's that kind of performance-based assessment, performance not of the machine but of the human who's using the machine to arrive to decisions. The one that I was saying was whether these explanations are useful at all is only to say that the person must be able to at least criticize the explanation. So he must be able to understand what is being said. So now, if you show a radiologist a GradCam image or something derived from a GradCam image, unless it sort of reflects something that he or she understands, he's not going to be able to do anything about it. So you can say whatever you want about it, but it's not really going to be terribly useful for the person. The other category of explanations, like the ones which fit things post hoc, like Lyme, for example,
Right.
Which has a certain, I mean, there's a certain sort of sense to some of it, in the sense that the idea that a highly nonlinear function in local parts could be explained by small linear models is not entirely unreasonable. But there are a number of other issues that doesn't take into account. For example, that you may have some prior which you're not taking into account. Most of the linear models are basically maximum likelihood based models which don't have any priors involved. So it may be the case that a slightly more complex linear model may be better as an explanation given the prior that you have. So that's may not be a categoric answer to your question, but these are the ways in which I would think about it anyway.
Sure. So for the current scenario, the way forward is to basically feed the model with the explanations that you are getting and see whether the performance drops or it's increasing. And
No, I wasn't giving the model any explanations. That I was giving models what I already know. So those weren't explanations. They were sort of, so in the area of something like drug design, a vast amount of stuff is already known about existing drugs, about targets, about toxicity, about solubility, all sorts of things. Now, it is feasible that a machine can discover all of these things for itself, just given the atom and bond structure and performing sort of quantum mechanical calculations for itself. But why would you want it to do that when you know all this stuff already? I mean, don't you want to get the most out of the machine by saying, look, we know all this stuff, don't bother re-deriving it. If you can use it, well and good. So that was the first part of my talk, was actually that that you want to provide things that that are probably useful to the machine. And if they are useful, then the machine's predictive power should increase, because it should be able to sort of see patterns that it couldn't see before. Because in the end, we are limited by sort of computational resources. We don't have infinite computational resources to be able to. So any assistance can't. So I think it's sort of unfair not to give a machine assistance. I mean, it seems unfair to me anyway. So.
Okay, got it. Thank you.
Okay.
Any more question?
The explanation
Sir Ashwin,
depends on the
yeah. Please go ahead. Somebody was speaking.
The explanation depends on the domain knowledge.
Please go ahead.
Right, the domain knowledge that is given. The domain knowledge is not constant. It keeps changing all the time. You can't say that you have a domain knowledge based on which you're trying to give an explanation. If the domain knowledge inconsistent, how do you arrive at the explanation that's right? How do you say that explanation is giving right? Because that's not very clear about domain knowledge. There could be a lot of noise than domain knowledge itself giving it.
So the question is the explanation in terms of the domain
in terms
knowledge?
Of domain knowledge, yes.
And
because domain knowledge may have a noise there. It will not be consistent. It will keep changing. At one point of time, you have one specific knowledge based on which you conclude something. It keeps changing. When you feed that system with the domain knowledge, which is not very consistent, changing all the time, the explanatory power of the model will not be good.
Yeah. Right? So let me give you again an answer in parts. So it's not that, although the examples that I showed you suggested that the domain knowledge had to be in a categoric logical form, that's not the only way it can be done, in the sense that there are sufficient advances now where domain knowledge can include probabilistic information along with logical information. So it's always been possible to include domain knowledge as probability distributions as prior knowledge. But the useful thing about the logical framework, in combining the logical framework with probabilities, is that it allows you to express fairly complicated distributions in a fairly straightforward way. So it is possible to take into account some of the uncertainties that you're talking about. I mean, inconsistency is that is a sort of worrying term, in the sense that if you're saying that the domain knowledge is inconsistent, or is it just uncertain? Inconsistent in a sort of logical world becomes a worrying thing, because from inconsistencies you can derive almost anything, or you can derive anything. So let's assume that when you say inconsistent, you don't mean really inconsistent. You just mean that it's sort of uncertain, and in a distributional sense. Sorry, I have a clock which will make a lot of noise right next to my ear. So, okay, that's done. That is one aspect of it, that it doesn't have to be a categoric, consistent, categoric domain knowledge. The second thing about the point about the explanation being in terms of whatever you've provided, and since that itself is not certain, then the explanation itself may not be sort of a very completely totally helpful. And that I agree. I mean, I think the point is that I think that this is not.
The expert themselves differ in the explanation.
Yes,
part of it.
I agree, and I think here I think the way forward is not to think of this as a one-shot thing, in the sense that you just have this happening once. I think what it means is that basically people will do this, having seen the explanations, they will do something like kind of conduct experiments, get more data, and then because if it is pointed out that based on what you've told me, this is what the data are suggesting, that should, I hope, trigger further sort of experimentation and further data collection and further refinement of the background knowledge. Maybe some things will become more certain, some things will become less certain, because some patterns become apparent, found by the machine, which will allow some of this at least the distributional uncertainty to change, if not if not become more categoric, it will at least allow certain sorts of distributions to change. So I think yes, the explanations are not intended to be the final answer. I think this is a sort of ongoing loop of which is why, for example, as I said, Rosking and co are actually considering directly talking to the real world with experiments, because some of the before they can propose some of these models as hypotheses or outputs, they need to check whether it is indeed the case that they're actually valid as such, or at least highly probable.
Professor Ashwin, I have a quick question.
Yes.
Bhaskar, you have any more question?
Which I have is that do we have a
please go
computational
ahead.
power? Or do you have computational power to do this kind of what you're talking about, the domain knowledge and explanation that you have to do it? That computation power is going to be very huge. Do you have this currently to be able to do that kind of task?
Do we have it here in Goa, or do we have it in the world somewhere?
In the world itself, that kind of.
No, I think we certainly these are real machines. So Rosking's machine is real, and it works.
Yes, if you look at drug design itself, the number of parameters, the amount of knowledge available is vast amount of knowledge. The model which would build it based on certain number of features, taking into consideration domain knowledge and the model, the predictive power which is based on domain knowledge. The computation is going to be very large computation. I don't know. I'm not sure about it.
No, so these are real machines. So Ross's machine does actually do all of this stuff. It sort of takes. I think the latest version takes sort of probabilistic domain knowledge, like I was saying. It builds models, and then several models are considered plausible. It then devises some experiments. So, for example, suppose the models are saying that if certain sorts of things are true, then this is very likely to be an active molecule, say, against a particular target. So then it actually tests against an existing database to see whether there are any similar molecules and whether they have high activity. So I mean, these are expensive machines, but they do have both the wet and the silicon-based experiment, model construction all integrated. So, I mean, I think the feasibility of such things it has been shown, the commercial day-to-day viability, I'm sure, for example, Pfizer and such companies will be looking at building such machines for sure. I mean, why would they not? Because they have a lot of money. So certainly the big institutions can do it. Whether smaller people like you and me can do it is maybe a little bit of time. But then who would have thought, that machines that that went past Jupiter and Pluto now look silly compared to our mobile phones. So these are all sort of starting points. I'm sure it will become very feasible and routine as we go along. So already there are many things that we do. We actually do interactively interact with our machines in much more ways than we used to before. So
Thank you.
Yeah, if there are no questions, let's conclude today's talk. Let's thank the speaker. Ashwin, it was nice of you to have agreed to come and give a talk. We look forward for your association with ACM Goa chapter in the future. Thank you, and thanks for all the audience who have made the time to come and attend the talk. We'll keep our tempo of at least once in a month. We'll try and organize some event, and we'll keep you informed through our website and through the emails. Okay. Thank you all, and let's conclude today's session. Maria,
Yes.
you want to say something?
Yes, sir. Thank you, sir. Thank you, everybody, for attending this session. Thank you, sir.
No,
And I hand over the mic to Veena now. Veena, you would like to add anything?
No, I would like to just thank Professor Ashwin formally. That's all. I think Professor Kamath already thanked. Thank you, Professor Ashwin, for introducing us to it's not IA, it's not AI, it is IA, which we need to focus in the present day. Thank you, sir.
Okay, good. Well, thank you very much. And I look forward to the other talks as well. So.
Thank you, sir.